Welcome to the topic asymptotes. Circle and ellipse are two familiar examples for curves which are limited in extent, whereas parabola and hyperbola are examples of curves which extend to infinity. In the latter case, it is sometimes necessary to inquire what happens to the tangent to the curve when the point at which the tangent is drawn moves further and further away from the origin. There are three possibilities, namely, the tangent may go further away from the origin, or it may keep oscillating, or it may tend to definite straight line. In the last case, the line to which the tangent tends is called asymptote. Thus, an asymptote of a curve is a straight line which touches the curve at infinity, but does not lie altogether at infinity. Definition: a straight line is said to be an asymptote of an infinite branch of a curve if, as the point P recedes to infinity along the branch, the perpendicular distance of P from the straight line tends to 0. For example, the line x is equal to a is an asymptote of the cissoid y square into a minus x is equal to x cube. It is easy to see that as the point Pxy moves to infinity, its distance from the line x is equal to a tends to 0. Determination of asymptotes. We know that the equation of a line which is not parallel to x-axis is of the form y is equal to mx plus c. The abscissa x must tend to infinity as the point Pxy recedes to infinity along this line. We shall now determine m and c so that the line y is equal to mx plus c may be an asymptote of the given curve. If p is equal to mp be the perpendicular distance of any point Pxy on the infinite branch of a given curve from the line y is equal to mx plus c, we have p is equal to y minus mx minus c all divided by square root of 1 plus m square. Now, p tends to 0 as x tends to infinity. Therefore, limit of y minus mx minus c is equal to 0, which means that when x tends to infinity, limit of y minus mx is equal to c. Also, y by x minus m is equal to y minus mx into 1 by x. Therefore, limit of y by x minus m is equal to limit of y minus mx into limit of 1 by x, which is equal to c into 0 is equal to 0, or limit of y by x is equal to m when x tends to infinity. Hence, m is equal to limit of y by x as x tends to infinity, and c is equal to limit of y minus mx as x tends to infinity. We have thus the following method to determine asymptotes which are not parallel to y axis. First one, find limit of y by x as x tends to infinity. Let limit of y by x as x tends to infinity is equal to m. Second, find limit of y minus mx as x tends to infinity. Let limit of y minus mx as x tends to infinity is equal to c. Then y is equal to mx plus c is an asymptote. The values of y will be different according to the different branches along which p recedes to infinity, and so we expect several values of limit of y by x corresponding to the several values of y, and also several corresponding values of limit of y minus mx. Thus, a curve may have more than one asymptote. This method will determine all the asymptotes except those which are parallel to y axis. To determine such asymptotes, we start with the equation x is equal to my plus d, which can represent every straight line not parallel to x axis, and show that when y tends to infinity, m is equal to limit of x by y and d is equal to limit of x minus my. The asymptotes not parallel to any axis can be obtained either way. Example: consider the folium x cube plus y cube minus 3axy is equal to 0 for asymptotes. Here, the given equation is of the third degree. To find limit of y by x, divide the equation throughout by x cube so that 1 plus y by x whole cube minus 3ay by x into 1 by x is equal to 0. Let x tends to infinity. Then we get 1 plus m cube is equal to 0, or m plus 1 into m square minus m plus 1 is equal to 0. Therefore, m is equal to minus 1. To find limit of y minus mx, when m is equal to minus 1. That is, to find limit of y plus x, we put y plus x is equal to p, so that p is a variable which tends to c when x tends to infinity. Putting p minus x for y in the given equation, we get x cube plus p minus x whole cube minus 3ax into p minus x is equal to 0, or 3 into p plus a into x square minus 3 into p square plus ap into x plus p cube is equal to 0, which is of the second degree in x. Dividing by x square, we get 3 into p plus a minus 3 into p square plus ap into 1 by x plus p cube into 1 by x square is equal to 0. Let x tends to infinity, then we have 3 into c plus a is equal to 0, or c is equal to minus a. Hence, y is equal to minus x minus a, or x plus y plus a is equal to 0 is the only asymptote of the given curve. Shorter methods for determining asymptotes. In practice, the rules obtained below for determining asymptotes are found more convenient than the method which involves direct determination of limit of y by x and limit of y minus mx. Here, we shall consider only the case of asymptotes parallel to the coordinate axis. Asymptotes parallel to the coordinate axis. Determination of the asymptotes parallel to y axis. Let x is equal to k be an asymptote of the curve, so that we have to determine k. Here, y alone tends to infinity as a point pxy recedes to infinity along the curve. The distance pm of any point pxy on the curve from the line x is equal to k is equal to x minus k. Limit of x minus k is equal to 0 when y tends to infinity, or limit of x is equal to k when y tends to infinity, which gives k. Thus, to find an asymptote parallel to y axis, we find the definite value or values k1, k2, etc., to which x tends as y tends to infinity. Then x is equal to k1, x is equal to k2, etc. are the required asymptotes. We will now obtain a simple rule to obtain the asymptotes of a rational algebraic curve which are parallel to y axis. We arrange the equation of the curve in descending powers of y, so that it takes the form y raised to m into phi of x plus y raised to m minus 1 into phi 1 x plus y raised to m minus 2 into phi 2 x plus etc. is equal to 0, where phi of x, phi 1 x, phi 2 x, etc. are polynomials in x. Dividing this equation by y raised to m, we get phi of x plus 1 by y into phi 1 x plus 1 by y square into phi 2 of x plus etc. is equal to 0. Let y tends to infinity. We write limit of x is equal to k. Then the equation gives phi of k is equal to 0, so that k is a root of the equation phi of x is equal to 0. Then the asymptotes parallel to y axis are x is equal to k1, x is equal to k2, etc. From algebra, we know that x minus k1, x minus k2, etc. are the factors of phi of x, which is the coefficient of the highest power y raised to m of y in the given equation. Hence, we have the rule: the asymptotes parallel to y axis are obtained by equating to 0 the real linear factors in the coefficient of the highest power of y in the equation of the curve. The curve will have no asymptote parallel to y axis if the coefficient of the highest power of y is a constant, or if its linear factors are all imaginary. Determination of the asymptotes parallel to x axis. As above, it can be shown that the asymptotes which are parallel to x axis are obtained by equating to 0 the real linear factors in the coefficient of the highest power of x in the equation of the curve. Example: consider the equation x square plus y square into x minus a y square is equal to 0. Here, the coefficient of the highest power y square of y is x minus a. Hence, the asymptote parallel to y axis is x minus a is equal to 0. The coefficient of the highest power x cube of x is 1, which is a constant. Hence, there is no asymptote parallel to the x axis. Asymptotes of the general rational algebraic equation. To determine the asymptotes of the general rational algebraic equations of the form un plus un minus 1 plus un minus 2 plus etc. plus u2 plus u1 plus u0 is equal to 0, where ur is a homogeneous expression of degree r in x and y. We write UR in the form UR is equal to x raised to r into phi r of y by x, where phi r of y by x is a polynomial in y by x of degree r at most. So, we have x raised to n into phi n of y by x plus x raised to n minus 1 into phi n minus 1 of y by x plus x raised to n minus 2 into phi n minus 2 of y by x plus etc. plus x into phi 1 of y by x plus phi naught of y by x is equal to 0. Dividing throughout by x raised to n, we get phi n of y by x plus 1 by x into phi n minus 1 of y by x plus 1 by x square into phi n minus 2 of y by x plus etc. plus 1 by x raised to n minus 1 into phi 1 of y by x plus 1 by x raised to n into phi naught of y by x is equal to 0. On taking limit as x tends to infinity, we obtain the equation phi n of m is equal to 0, which determines the slopes of the asymptote. Let m1 be one of the roots of this equation so that phi n of m1 is equal to 0. We write y minus m1x is equal to p1, that is y by x is equal to m1 plus p1 by x. Substituting this value of y by x, we get x raised to n into phi n of m1 plus p1 by x plus x raised to n minus 1 into phi n minus 1 of m1 plus p1 by x plus x raised to n minus 2 into phi n minus 2 of m1 plus p1 by x plus etc. plus x into phi 1 of m1 plus p1 by x plus phi naught of m1 plus p1 by x is equal to 0. Expanding each term by Taylor's theorem, we get x raised to n into phi n of m1 plus p1 by x into phi n dash of m1 plus p1 square by 2x square into phi n double dash of m1 plus etc. plus x raised to n minus 1 into phi n minus 1 of m1 plus p1 by x into phi n minus 1 dash of m1 plus p1 square by 2x square into phi n minus 2 double dash of m1 plus etc. plus x raised to n minus 2 into phi n minus 2 of m1 plus p1 by x into phi n minus 2 dash of m1 plus p1 square by 2x square into phi n minus 2 double dash of m1 plus etc. is equal to 0. Arranging terms according to descending powers of x, we get x raised to n into phi n of m1 plus x raised to n minus 1 into p1 phi n dash of m1 plus phi n minus 1 of m1 plus x raised to n minus 2 into p1 square by 2 into phi n double dash of m1 plus p1 phi n minus 1 dash of m1 plus phi n minus 2 of m1 plus etc. is equal to 0. Putting phi n of m1 is equal to 0 and then dividing by x raised to n minus 1, we get p1 into phi n dash of m1 plus phi n minus 1 of m1 plus p1 square by 2 into phi n double dash of m1 plus p1 phi n minus 1 dash of m1 plus phi n minus 2 of m1 into 1 by x plus etc. is equal to 0. Let x tends to infinity. We write limit of p1 is equal to c1. Therefore, c1 into phi n dash of m1 plus phi n minus 1 of m1 is equal to 0, or c1 is equal to negative of phi n minus 1 of m1 divided by phi n dash of m1 if phi n dash of m1 not equal to 0. Therefore, y is equal to m1x minus phi n minus 1 of m1 divided by phi n dash of m1 is the asymptote corresponding to the slope m1 if phi n dash of m1 not equal to 0. Similarly, y is equal to m2x minus phi n minus 1 of m2 divided by phi n dash of m2, y is equal to m3x minus phi n minus 1 of m3 divided by phi n dash of m3 etc. are the asymptotes of the curve corresponding to the slopes m2, m3 etc., which are the roots of phi n of m is equal to 0 if phi n dash of m2, phi n dash of m3 etc. are not 0. Exceptional case. Let phi n dash of m1 is equal to 0. If phi n dash of m1 is equal to 0, but phi n minus 1 of m1 not equal to 0, then the equation c1 phi n dash of m1 plus phi n minus 1 of m1 is equal to 0 does not determine any value of c1, and therefore, there is no asymptote corresponding to the slope m1. Now, suppose phi n dash of m1 is equal to 0, which is equal to phi n minus 1 of m1. In this case, the equation c1 phi n dash of m1 plus phi n minus 1 of m1 is equal to 0 becomes an identity, and we have to re-examine the equation p1 phi n dash of m1 plus phi n minus 1 of m1 plus p1 square by 2 into phi n double dash of m1 plus p1 phi n minus 1 dash of m1 plus phi n minus 2 of m1 into 1 by x plus etc. is equal to 0, which becomes p1 square by 2 into phi n double dash of m1 plus p1 into phi n minus 1 dash of m1 plus phi n minus 2 of m1 into 1 by x plus etc. is equal to 0. On taking limits as x tends to infinity, we see that c1 is a root of the equation c1 square by 2 into phi n double dash of m1 plus c1 into phi n minus 1 dash of m1 plus phi n minus 2 of m1 plus etc. is equal to 0, which determines two values of c1, say c1 dash and c1 double dash, provided that phi n double dash of m1 not equal to 0. Thus, y is equal to m1x plus c1 dash, y is equal to m1x plus c1 double dash are the two asymptotes corresponding to the slope m1. These are clearly parallel. This is known as the case of the parallel asymptotes. Note: the polynomial phi n of m is obtained by putting x is equal to 1 and y is equal to m in the highest degree terms x raised to n into phi n of y by x, and phi n minus 1 of m, phi n minus 2 of m etc. are obtained from x raised to n minus 1 into phi n minus 1 of y by x, x raised to n minus 2 into phi n minus 2 of y by x etc. in a similar way. Example: consider the curve x cube minus x square y minus x y square plus y cube plus 2 x square minus 4 y square plus 2 x y plus x plus y plus 1 is equal to 0. Putting x is equal to 1 and y is equal to m in the third degree and second degree terms separately, we get phi 3 of m is equal to 1 minus m square plus m cube, which is equal to 1 minus m into m square into 1 minus m, which is equal to 1 minus m square into 1 minus m, that is equal to 1 minus m whole square into 1 plus m. Phi 2 of m is equal to 2 plus 2m minus 4m square. The slopes of the asymptotes given by phi 3 of m is equal to 0 are 1, 1 and minus 1. To determine c, we have c into phi 3 dash of m plus phi 2 of m is equal to 0. That is, c into minus 1 minus 2m plus 3m square plus 2 plus 2m minus 4m square is equal to 0. For m is equal to minus 1, this gives c is equal to 1, and therefore, y is equal to minus x plus 1 is the corresponding asymptote. For m is equal to 1, the equation becomes 0 into c is equal to 0, which is identically true. In this exceptional case, c is determined from the equation c square by 2 into phi 3 double dash of m plus c into phi 2 dash of m plus phi 1 of m is equal to 0. That is, c square by 2 into minus 2 plus 6 m plus c into 2 minus 8 m plus 1 into 1 plus m is equal to 0. For m is equal to 1, this becomes 2c square minus 6c plus 2 is equal to 0, which implies c is equal to 3 plus or minus root 5 divided by 2. Hence, y is equal to x plus 3 plus or minus root 5 divided by 2 are the two parallel asymptotes corresponding to the slope 1. We have thus obtained all the asymptotes of the curve. Some deductions. The number of asymptotes of an algebraic curve of the nth degree cannot exceed n. The slopes of the asymptotes which are not parallel to y axis are given as the roots of the equation phi n of m is equal to 0, which is of degree n at the most. In case the curve possesses one or more asymptotes parallel to y axis, then it is easy to see that the degree of phi n of m is equal to 0 will be smaller than n by at least the same number, hence the result. The asymptotes of an algebraic curve are parallel to the lines obtained by equating to 0 the factors of the highest degree terms in its equation. Let m1 be a root of the equation phi n of m is equal to 0, so that the line y minus m1x is equal to 0 is parallel to an asymptote. By elementary algebra, y by x minus m1 is a factor of phi n of y by x, and hence y minus m1x is a factor of x raised to n into phi n of y by x, that is un. Also conversely, we see that if y minus m1x is a factor of un, then m1 is a root of phi n of m is equal to 0. In case the highest degree terms contain x as a factor, then a little consideration will show that the curve will possess asymptotes parallel to x is equal to 0, that is to y axis. Let me summarize the major points of this session. A straight line is said to be an asymptote of an infinite branch of a curve if, as the point P recedes to infinity along the branch, the perpendicular distance of P from the straight line tends to 0. To determine asymptotes which are not parallel to y axis, we may proceed as follows. Find first one limit of y by x as x tends to infinity. Let limit of y by x as x tends to infinity is equal to m. And second, find limit of y minus mx as x tends to infinity. Let limit of y minus mx as x tends to infinity is equal to c. Then y is equal to mx plus c is an asymptote. The asymptotes parallel to y axis are obtained by equating to 0 the real linear factors in the coefficient of the highest power of y in the equation of the curve. The curve will have no asymptote parallel to y axis if the coefficient of the highest power of y is a constant or if its linear factors are all imaginary. The asymptotes which are parallel to x axis are obtained by equating to 0 the real linear factors in the coefficient of the highest power of x in the equation of the curve. The number of asymptotes of an algebraic curve of the nth degree cannot exceed n. The asymptotes of an algebraic curve are parallel to the lines obtained by equating to 0 the factors of the highest degree terms in its equation. Now, you may try to answer the following questions. Find the asymptotes of the curve x minus y plus 1 into x minus y minus 2 into x plus y is equal to 8x minus 1. Second one, find the asymptotes parallel to the coordinate axes of the following curves. 1. Y square x minus a square into x minus a, and 2. A square by x square plus b square by y square is equal to 1. Third one, show that the curve x raised to 4 plus y raised to 4 is equal to a square into x square minus y square have no asymptotes. Fourth one, find the asymptotes of x minus y whole square into x square plus y square minus 10 into x minus y into x square plus 12 y square plus 2x plus y is equal to 0. For your further study, you may go through the books given here. First one, Differential Calculus by Shanti Narayanan, Sultan Chand and Company, New Delhi, 2003. Second one, Differential and Integral Calculus by N. Piskunov, Peace Publishers, Moscow. Third one, Calculus, 9th edition by George B. Thomas, Rosal Finney, Pearson's Education, New Delhi, 2002. Hope that you have enjoyed this session. We will meet again with another topic. Thank you.